Suppose we were asked to differentiate y is equal to x cubed sine x. Now, at the moment, we can't do that because it's the product of two functions. X cubed is the first function, let's call it u, and sine x, the second function, let's call that v. All we do know is our rule from first principles about a single function where we worked out this formula. It relies on the fact that h will go to 0 and we can work out the limit of the right-hand side as h does go to 0 and simplify the equation accordingly. Well, what I've done here is I've replaced our simple function fx with the product of two functions. So fx is u and gx is v. We'll come to solve this equation later once we've worked through this. But the right-hand side of this equation is too complicated at the moment, but with a little bit of algebraic manipulation, this will turn into a really useful rule that will be incredibly simple to use for any example of a function which is the multiple of two other functions. The proof of this is not in the syllabus for A-level, but I always think even if you just watch this once, it's worth it because you can then take the rule and say, yeah, one day I saw it work. Now the simplification relies on a little trick, and the trick is this. If I add fx plus h multiplied by gx to the top line, which of course we'd have to subtract straight away or we'd change the value of the right-hand side. So this is minus fx plus h gx. Effectively, they cancel out. But if I add that to the top line, I get this. Now, you'd be quite right to say, well, what on earth use is that? But look at the first two terms. I've got a common factor of fx plus h sitting there. And look at the second two terms. I've got a common factor of g of x. You can see why I'm not choosing to write these all out all the time. But here we are, look. Here's our common factor, fx plus h. And here's our common factor, g of x. I've duplicated the limits as h goes to 0, and I've applied it to all separate terms with an addition sign in between. So let's think about this term in the front here. Well, the limit as h goes to 0 of fx plus h is simply fx. And this term here, the limit as h goes to 0 of g of x plus h minus gx over h, if you compare that with our definition of differentiation from first principles, this is just the differential of gx. So this will be g prime of x multiplied together. And there's our plus. The limit as h goes to 0 of g of x is simply g of x. H doesn't come into it. And this second term here is identical to our definition of the differential of fx. So this is f prime x. Effectively, we've got our product rule. Here we are. This is what we originally wanted to work out, the differential of one function multiplied by another, fx multiplied by gx. That's duplicated here. And this is equal to fx, and then the differential of gx, g prime x, plus g of x multiplied by the differential of fx. You won't be remembering it that way, but you will be remembering it this way. If y was equal to u multiplied by v, and we wanted dy dx, therefore we want the differential of u times v over dx, it works out to this very memorable formula. U multiplied by dv dx plus v multiplied by du dx. So comparing it with our equation above, u would be equal to f of x, and v would be equal to the second function, g of x. And an even simpler version of this would be dy dx is equal to u dv plus v du. And that's the version most students learn and remember. So let's apply it to the example I posed right at the beginning of the tutorial here. We've got x cubed as u and sine x as v. So let's just write that out. U equals x cubed and v equals sine x. Okay, we want du dx, which is equal to 3x squared. And dv dx, the differential of sine, is cos x. Well, we've got all the constituent parts of our remembered product rule. So we can say if y equals x cubed sine x, dy dx is equal to, we've just got to pick these off our table, u, x cubed, dv dx, cos x, plus v, write down v, sine x, du dx, which is 3x squared. So if you wanted to just make this a little bit neater, the first term's okay. This is x cubed cos of x plus, and I think put the 3x squared here, sine x. And maybe for one more line of simplification, you can take an x squared out, and this is x cos x plus 3 sine x. And there's your answer in its most simple form. So we've now got the product rule, which enables us to handle even more complex function arrangements and differentiate them easily. You won't be surprised there is a quotient rule coming up. I won't do the proof for that, but that again enables us to differentiate one function divided by another. So they pair up. And I hope, as I say, if you only just see that proof once, at least the formula hasn't been plucked out of thin air. And that's it.